So our last 15-minute speaker before the discussion is Dee Lee, and it looks like he's changed his title, so I'll read it off the board. It says Fast, Heiles, and Dark Gas.
It's similar content. So yes, I'll be talking about fast, and I put Heiles here in his favorite color, pink. And most of astronomy looking back in time. My talk will look towards the future, but a little bit past dinner, but not too distant. So we're building this fast. The biggest fully mobile telescope is GBT, which basically, well, everything on this graph is to scale, so we're basically moving the Statue of Liberty. And then we have the stationary telescope, Arecibo, and this is fast. A couple months ago, you will see more picture of it. So how big it is? If you put in fried rice, so everybody in the world gets 2 bowls of rice. But if you have to drink wine, you have to share a bottle with someone else. And we have initial budget of a little more than 600 million RMB, and the final budget is 1.15 billion yuan, or about $200 million. And to realize this large collecting area, we have this cable mesh network. So each triangle is about 11 meters on one side, and you're connecting 6 such triangles, and you pull down the connecting knot to the ground. And by moving it about a meter, that is enough to change it from a 300-meter radii sphere into a 300-meter parabola. But the challenge is to move it in real time and know where you're moving. So we have this measuring towers, and each one of them holds a laser total station, and we're shooting laser at the targets. So this is a picture taken from my iPhone, and at the time of the picture, there's no lights. So what you're seeing here is just a single flash, and you see the reflected lights from those optical targets. And you can play with this when you get to the site. And it's still dark, although it's not necessarily so because we are a radio telescope. So this is a typical day on the site, and this is too slow for the talk. So this is what we have been doing for the past 5 years or so. And it's like a Russian Tetris game. We have this crane and shooting down the panels. It looks easy. Right as we are speaking, we are past 98% finished, so it's coming really quick. So to put it in context, we have 100-meter GBT, 300-meter Arecibo, and we will realize the largest collecting area of the best absolute sensitivity below 3 gigahertz band with 4,500 panels and more than 2,000 actuators. And we'll do everything from exoplanet to cosmology. But the point I want to point out is the flexibility, which means it's still a single dish. It's the most cost-effective way, still realizing the absolute sensitivity. So you can still able to bring your own instrument and exchange it for your innovative ideas, which is becoming exceedingly hard for large arrays like ALMA. Not only you have to get much more money to change all the receiver system, but the harder part is to convince more than 1,000 worldwide astronomers that your idea is worth stopping the whole array for 3 months or so. So this is, according to the Nature magazine, at the end of 25, this is one of the things looking forward to in terms of space exploration. And we cover 70 megahertz, 3 gigahertz, and pulsars, H1 line, and molecular lines. And we will shoot for open sky, and we're starting to building up this international collaboration network and looming large on the west coast of the United States is Carl. This is a ISM conference, but did you know that Carl Heiles was one of the co-discoverers of millisecond pulsar? So this is like a homage to him. So by collaborating with George Hobbs, From Parks, we managed to find 2 new millisecond pulsars. Well, I hope to get a sound. So, can we turn that on? Sorry. All right. It doesn't work yet. Try again. So this is the millisecond pulsar downsampled 80 times and mix it with other 23 pulsars. And the short view here is the dispersion, so the signal scattering through the interstellar electrons. So that particular millisecond pulsar is 1.84 millisecond period. It's the fastest spinning pulsar in that globular cluster and rank 12 among all the pulsars. So we know how to search for pulsars, and we'll do this by bunches with fast. So come to the topic of conference today. I don't have to say anything about it. So it's dark gas. It becomes a fact of life. And like a lot of other things, nothing is really new in ISM field. So this is even in the textbook. It's a Bruce Ring's relatively new book. So in the intermediate extinction region, when the H+ transition into hydrogen, into molecular hydrogen, CO comes relatively late. So you actually have ionized carbon throughout this intermediate region, and part of it have molecular hydrogen with self-shielded earlier than the CO. So that's exactly what CO dark molecular gas is. But if you have to look into the chemistry, I never understand this good enough. If you have to pick out the chain, if you form H2 first, then through cosmic ray and a slew of charge exchange or neutral charge exchange, quick reactions, you will quickly get to OH and HCO plus before you get to sort of stable population of CO. So what about OH? If you look in the past, well, OH is the first discovered radium molecules. But it's very rare you find large OH maps. And it's kind of depressing. This is just one example. It's looking for OH in nearby galaxies and spent about 1,000 hours of Arecibo, and they found none. And we think the reason is actually just excitation. So if you look in emission, essentially you have to look at the difference between the background and the excitation. So if the excitation of OH is close to the background excitation, you'll see nothing. You're looking at a little dim light bulb against a bright screen, and that bright screen is just your CMB along most of the line of sight. So to actually see that, you need absorption. So this is that seminal paper by Heiles and Troland. And so we bring Carl to NAOC, and Carl bring his very nice absorption technique. This is Carl at the fast side in 2012, and again in 2015, interviewing the same security force on site, both sort of getting a little bit more senior, but both think very functional. And the thing we realized is Carl, not published in that paper, but he took OH data simultaneously with H1. So along with Carl, we also take more CO data. So you see these 3 representative line of sight toward 3 quasars. This is just a garden variety molecular cloud. You see H1 in absorption, OH in absorption, and every CO lines. This is a cold neutral medium. You see H1 in absorption and nothing else. But in the middle, you sort of see H1 and OH and no CO. That is the definition of dark molecular gas. And we did this statistically, well, as much as we can, found about 40 such line of sight, and H1 spreads through the column density, and once you get the self-shielding threshold of H2, you start to get both CO and OH, and they are statistically about the same. So on that quantity, you get at least as much as sort of CO dark molecular gas as CO sort of trace. So the plan for FAST, together with Carl and a lot of the attendees of this conference, Naomi and other people, is to extend the Millennium Survey with FAST by one order of magnitude. We can do 800 quasars of similar studies. So this is just quickly another project we're working on together and just accepted by ANA, is to looking through the C+ cloud that detected by Herschel of this particular Gauss C+ large program that I'm also involved in, looking at those C+ cloud without CO, and also look at those clouds, try to identify those in H1 self-absorption. So this little dark cloud have that 3 qualities. By that, we can limit excitation by analysis of H1 self-absorption, or so-called H1 narrow self-absorption that Goldsmith and I developed from beginning of 2000, and calculate the quantity of H2 by constraining the excitation of the C+ line, because it's compared to the cold gas, it's way above the ground state. So it really requires extra excitation. And then this is just a definition of CO dark molecular cloud. And we found about 42 such CO dark C+ emitting and H1 in absorption sort of dark molecular cloud. And this is the distribution of the column density versus a fraction of dark molecular gas. And this is just a empirical, it's sort of to the first order, a empirical formula. But what's a little bit strange or surprising is that there's this bunch of about 9 clouds with large extinction. So that's large enough for self-shielding of CO. But the CO abundance in this cloud is lower than 2 orders of magnitude lower than the canonical value of 10⁻⁴. So this is a very good candidate of this transition cloud. So they are either just forming CO, or it's in another picture. So usually we think that the cloud formed in this simplistic way from ions to atoms to molecules. And there's also an alternative picture suggested very nicely by Pringle and Allen that you may have sort of little clumps of H2, that's exactly those CO dark molecular clouds throughout the galaxy. So that shortened the time scale to form molecular clouds and star formation. So back to the Carl and FAST. So this is the first FAST conference back in 2012. Carl is right in the middle. This is 2015. Carl is here. And this is Carl study very carefully of the food and looking suspiciously at the food, and finally triumphantly with the food. And this is, we go to the site with Tim, Enrique, but by looking at the hand gesture, undoubtedly the leader is the future generation. So after 5.5 years, I'm committed to the first light date of September 25th. And we're here celebrating the pioneering work of Professor Crutcher and Professor Heiles. Looking toward the future, the next few years will be really exciting for FAST and for the radio community. We will have thousands of bugs, and nothing will work perfectly at the first time or even the first 10 times, but it does have revolutionary prospect. So I guess also we are hiring 3 to 5 postdocs each year. So for the younger generation, I'd like to quote Charles Dickens: "This is the best of time, this is the worst of time. But for the younger generation, this is your time." So, thank you.
Okay, questions for Dee? So can you tell us what some of the pilot observations questions are going to be?
Yes, so so there are a couple of quick things. We'll be looking for new pulsars, and we both targeted and also drift scans. Also looking for OH megameters, and looking at a couple of quasars to doing the absorption study. And after the initial commissioning, the big driver will be a drift scan, all northern sky, a commensal survey of both H1 galaxies, pulsars, galactic H1s, fast radio bursts, and SETI. But that is still being worked out because that requires the 19-beam focal plane array to function properly. Also, there will be some hard negotiation between each communities because for a major telescope that has never been done, the pulsar community and the galaxy, H1 galaxy community never come to terms of how the survey should be done, but it's sort of necessary for us, just given the time constraint.
You didn't mention Zeeman as one of your target science goals. Is that not included?
Not in the first 2 years. So Carl has committed to come on site in July and to help us to plan that out. But that will be as always, one of the most difficult aspects. And I don't know how to calibrate the polarization yet, because we are looking at a changing telescope and it's non-repeating. So we probably need some external source to calibrate properly, maybe using pulsars, but the things has to be tested out. But if it, in concept, because it has much cleaner beam, it has great potential in doing Zeeman, in L-band particularly.
Okay, was there one more quick question? Right, from Blakesley, sure, and then we'll get ready for the discussion.
So coming from the younger generation, how can we use this telescope? Is there going to be an open proposal system?
Yes, so we both in the project proposal and also in the operation plan, we will stick to the open sky policy. But in reality, in the next 2 years, we're mostly commissioning. And once they get to the operation stage, it will be divided roughly half and half a large project driven by science teams to do like drift scans surveys that serve multiple purposes. The other half, we will try to give as much as we can to the PI-driven individual projects.
Okay, great. Let's thank you again.
Okay.